Now that you know what power is, you can relate power to intensity. But in order to do that, you're going to need to know what a wavefront is. So a wavefront is a surface or curve on which all points have the same phase. So let's think about an example of this. Imagine moving your finger up and down in a bath or a pond. In this case, you'd see a wave pattern similar to this simulation here. You can see that the waves are traveling out as circles. So each of these circles that you see is a wavefront. Now, as you can see here, as you get further from the source, where the point is moving up and down, the intensity of the waves, that's the height and amplitude of the waves, is related to the intensity, as we'll see, drops off. So what's happening in this case is that the waves, as we've said, are carrying energy. So the source, your finger in this case, is supplying power. Now, on average, you're supplying a constant amount of power. So that is over one complete cycle, you're supplying the same amount of power each time. Now, as that power is carried away from your source, if you imagine those wavefronts, each of those wavefronts has that same amount of power because we're not creating power or energy from anywhere. It's being carried away from that source, and as it's carried away, those wavefronts are spreading out, and so the area over which your power is being spread is getting larger and larger as you move away from the source. So this is telling you that the amplitude of those waves, which you can see, and the intensity of the waves is decreasing as we're getting further away from the source. Now, in three-dimensional space, a similar thing happens. So imagine now a light globe or even a star if we want to consider out in space. The star is supplying power at a constant rate from its surface. And in this case, it's going out in all three dimensions. And so the surface over which that power is being sped is a sphere in this case. And the surface area of a sphere is given by the equation 4 pi r squared. And so that tells us how much that power is being spread out. So to relate intensity to power, we use the formula I is equal to P on A, where I stands for the intensity, P is the power, and A is the area. So for a three-dimensional object, we've got that the area over which this power is being spread is a sphere, and so A in this case is 4 pi r squared. So for a three-dimensional object, we've got that the intensity is equal to P over 4 pi r squared. P is the power in watts, 4 pi r squared is the area, which is in meters squared, and intensity is the power per meter, the watts per meter squared. So let's try a problem using this equation now.
Okay, so the question is, a 60-watt light globe sends out light isotropically in 3 dimensions. What is the intensity of light 1.0, 2.0 and 3.0 meters from the globe? So in order to answer this, we'll need to use the equation the intensity is equal to the power over the area. Now in this case, the light is being sent out isotropically, which means the same in all directions, in 3 dimensions. So in that case, as it's spreading out equally in every direction, it's going to spread out over the surface of a sphere. So A is going to be the surface of a sphere, which is 4 pi r squared. So now we can calculate this at the different distances. So the first distance is 1 meter. So let's call this I1. The power supplied is 60 watts, and then we divide by 4 pi times 1 squared. And solving this on the calculator, we end up with 4.8 watts per meter to the minus 2. Now we need to calculate it at 2 meters. Now when we double the distance, because the intensity is proportional to 1 over the radius squared, which is the distance squared, we'd expect if we doubled the distance, we'd end up with a quarter of the intensity. So let's just calculate it to check that. So the power 60 divided by 4 pi times 2 squared, and solving that on the calculator, we get 1.2 watts per meter to the minus 2, which is indeed a quarter of the intensity at 1 meter. Now the intensity at 3 meters, in this case, we've times the radius by 3. So to get the intensity, we'd expect to divide it by divide it by 3 squared, which is divided by 9. So we'd expect our answer to be 1/9 of 4.8 watts per meter. So we've got 60 divided by 4 pi times 3 squared. And solving that on the calculator, we end up with 0.53 watts per meter to the minus 2, which is 1/9 of this. So you can see with all these answers, I've given them to 2 significant figures, as 1, 2, and 3 are all given to 2 significant figures, and 60 watts, that's either 1 or 2, and we should assume 2. Okay, how about you try a problem now?